So Bhupal graduated from University of Maryland. During that time, we used to collaborate. After that, Bhupal went to England for his first postdoctoral position, then to Germany. And this year, he has joined Washington University as an assistant professor. So,
thank you. Thanks for the kind invitation. My first time here in Texas. I thought it's a good place to start in Texas. I'll be talking about some recent work I did with Manfred Lindner and his student Sebastian Omer at the Max Planck Institute in Heidelberg, where I was a postdoc, last postdoc there. So this is like kind of a new topic for me, so I'm not an expert on this, so I should start with this disclaimer that you guys probably know, maybe know more than me on this topic, so maybe I'll try to learn something from you, from the discussion. So please feel free to interrupt me and we can discuss and kind of make it informal. I'll propose that we can use gravitational waves as a new probe of dark matter, and not all kinds of dark matter can be probed in this way. So we'll see only certain kinds of dark matter which form kind of a condensate in the early universe. They can be probed using gravitational waves, and they can be done using the current LIGO sensitivity. That's what I'll claim. This is the reference in case you're interested. Last month. So let me start with the very basics. Of course, everybody knows here, but just to set the stage, we know that the dark matter consists of like 26% to 27% of the energy deposit of the universe, and the relative density has been very precisely measured, and it's the latest number from Planck. It has to be stable on a cosmological time scale to be dark matter, so it can be either absolutely stable or at least it has long lifetime, much larger than the age of the universe to be dark matter. And it must have gravitational interactions because that's what we see. But we do not know whether it has other interactions or not. Then this is pretty much we know about dark matter actually, and everything else is unknown. So we can go and speculate on different kinds of dark matter models. But there has been this old dark matter hypothesis, which is very successful, explaining large-scale structure. Just to give an example, this is a simulation picture. I don't know if you can turn off this light. Yes. I have some pictures. Thanks. Okay, great. Yeah. Thanks. So this is just I've taken a picture of n-body simulation from this group from Zurich, where they saw a comparison between three different kinds of dark matter: hot dark matter, warm, and cold. And this is the picture in the early universe, and like high redshift, and this is the picture today's universe. And so you can see that they're very different from each other, and then you can compare this with observations, and then we can confirm that looking at large-scale structure that this is the kind of dark matter that we should have in the theory. So this works very well at large scales. This is like extragalactic scales. But if you go down to the galactic scales or subgalactic scales, then there are some issues which cold dark matter hypothesis cannot explain. So this is, of course, this is not a convincing evidence that the cold dark matter hypothesis is wrong, because this works so well at large scales. So and there have been many other alternative proposals also how to make it work, even at galactic and subgalactic scales, for example, including variance in the simulations and looking at other supernova feedbacks or black hole feedbacks, all these things. But yeah, so in this talk I'll argue that there might be another alternative that we can that can resolve these small scale structure problems. So what are these small scale structure problems? So I'll discuss three of them. One is known as the core versus Cusp problem. So this is a picture I've taken from this particular paper where they looked at some dwarf satellite galaxy survey, and these are the data points, and this is the radius and this is the density. This is what you would get from predictions from cold dark matter simulations. This will try to, so this will basically predict kind of a steeper cusp around at low radius or towards the center of the halo, but you would see less number of, you would see kind of a flatter spectrum towards the center. So just to put it in quantity, so you predict that this power R should be -1 from simulations, but in observations you kind of get like a flatter spectrum. So this is more kind of a factor. So this is one problem which the usual cold dark matter hypothesis doesn't address. And there's another problem which is known as the missing satellite problem. So again, you compare the simulations with observations. So this is the simulation from the Aquarius project for cold dark matter. And so this is like an QSI's halo, and you can see like there are a lot of substructures here, so these are subhalos. But if you compare with observations, this is an observation I think in Andromeda, and here you see much fewer satellite galaxies than you predict in simulations. So what about the other missing satellites? So this is one issue. And the third one is kind of related to the second one, is that is known as the too big to fail problem. So if you look at the masses of this, the function of the distance from the galactic center, from the center of the halo, you would get the simulation should predict something here. But if you look at the data, then you see that these are not so massive as predict in simulations. So again, so this is like so you predict more massive subhalos than you would see. So again, all these problems can be resolved by invoking some additional things that are not present in the simulations. But one possible hypothesis is that the dark matter could be, it's not collisionless and pressureless, rather it has some self-interactions. And these self-interactions would make it more compatible with observations. Okay, so and how is that? If you look at, again, the same figure that I showed on the previous slide, you look at the density profile. So if you have self-interactions, then at smaller scales, so it would tend to make it more it would tend to make the density more flatter, just because it has this self-interaction. So it doesn't let it grow this 1/r kind of behavior. That would happen for collisionless dark matter. But if you go to higher scales, then this would behave exactly same as like a cold dark matter. So in this sense, it is compatible with large scale structure data, and also it's compatible with the smaller scales. And the same thing you can do with this missing satellite issue, that now because of the self-interaction, the smaller scale structure formation will be kind of suppressed. Again, just because you have this self-interactions. But at higher scales, it would be exactly similar to the cold dark matter, but only in smaller scales, you would see kind of less number of structures. So this again explains the missing satellite, and also explains the two big different problems. Okay. So I would take that as my motivation, and then I would propose a new method to probe the self-interacting dark matter and using gravitational waves. Okay. So basic idea is very simple. So you let's assume that you have a source of gravitational waves, and then en route to Earth, it encounters a self-interacting dark matter halo. And just like light passing through a medium slows down, the same thing would happen for gravitational waves. You have a refractive index, and then gravitational wave will slow down when it passes through this dark matter halo. But usually this effect is very small, because gravity is very weak interaction, is the weakest interaction. So this effect is very, very small at some unobservable level for ordinary dark matter halo, or for that matter for any ordinary matter. But there is a significant enhancement in presence of some long-range correlations. And this kind of long-range correlations are possible if the dark matter halo is made up of some kind of like a Bose-Einstein condensate. Okay, so this is the this is the line of argument that I follow. So the first assumption is that we have a self-interacting dark matter halo, and the second assumption is that it has a long-range correlation. That means it forms a condensate. In that case, we can use this method like we can measure the change in the speed of gravitational waves as it passes through this medium, and then we can constrain this scenario, or we can probe this if we find some observable change. So okay, the Bose-Einstein Condensate, of course, it has been measured, has been observed in labs, and this is a macroscopic quantum phenomenon, and people have got Nobel Prizes for this. So then our assumption is that why not that it could happen in nature? Okay, so nature might be also doing it for dark matter halos. If they are scalar particles, then there could be some ambient conditions where you can form a VC in the dark matter halo. And this idea actually came right after this was observed in labs by people from Taiwan, and then later it was followed up by many other groups. Okay. So there are two different kinds of VC halos that people have studied. One where you do not have any self-interaction. Okay. In that case, you have to balance the gravitational attraction by some repulsive force, and that is automatically given by the quantum pressure. But this works only if the mass is very small. It turns out that only if its mass is around like 10 to minus 22 electron volt, then the quantum pressure is enough to balance against the gravitational pull, and then this forms a stable halo. Okay. This scenario is known as fuzzy dark matter. Okay. And yeah. So by the way, this is not such a crazy idea. Many people have worked on this, and in fact, today there was a paper by very distinguished people, including Ed Witten, who wrote a paper on this fuzzy dark matter. So this is kind of a very well-studied idea. Okay. So this actually, you can see that, kind of roughly see this mass where y is so small. So the idea is that the de Broglie wavelength has to be roughly of the size of the galactic halo or smaller than that. And so the smallest halo size is roughly 1 kiloparsec. That's the size of the dwarf spheroidal galaxies, the smallest one. So if you compare the de Broglie wavelength, which is just 2 pi over mv in units h bar equal to 1, if you compare that with the 1 kiloparsec, you get a lower limit on the mass, because the velocity of the dark matter particles in a halo is kind of, so if you take the virialized velocity distribution, it's 10 to minus 3. And then you can just plug in the numbers, and you find that this m is actually 10 to minus 22 electron volt. So that's kind of the lower limit for any dark matter particle mass in a condenser. And then if you include a repulsive self-interaction, then you can actually extend this mass range to higher values, and you can go all the way up to electron volt, more or less. And why electron volt and not more than that? Again, you can apply this very rough argument that the de Broglie wavelength must be larger than the interparticle spacing. Otherwise, this won't behave like a condensate. Okay, so this is a basic condition for it to form a condensate, is that the de Broglie wavelength must be larger than interparticle spacing, which is basically n over the mass over the density to the power 1/3. And using that, you can get an upper limit on the mass, which is electron volt. Now, in this here, the most important thing to remember is that this has to be repulsive self-interaction. If you have an attractive self-interaction, it will destabilize the system, because gravity is already attractive, and if you add another attractive term to that, then it will completely destabilize the system. Then this is the usual Jeans gravitational instability, and then it won't form a halo. It will collapse to much smaller structures like a boson star or some mini cluster or something like that, which is like kilometer size, right? Not kiloparsec size. Okay, so that's why it's very crucial to have a repulsive self-interaction, to have this long-range correlation, and to have like halo-size object which behaves like a VC, okay, where all the particles are basically in the ground state of the potential. Okay. So this is something that has not been appreciated so much previously. In fact, Pierre Sikivi, who is a very strong proponent of axion dark matter, he has been claiming that you can form VC with axions. But if you look at axion potential, you find that this is actually attractive potential. So for axions, it's actually impossible to form a VC unless you modify the usual axion potential and you add some other terms. And this has been shown recently by this paper by Alan Guth and his collaborators from MIT, and also shown by another paper by Gigi Fan. So this is very crucial
like
point.
10 to the power minus 22 EV, people try to use the axion, light axions to.
Yeah, so there it's
fine.
fine because they're assuming that there is no interaction.
No internet.
Or the interaction is very, very small. So that only quantum pressure is enough to do that. But if you do QCD axion, then you need to have 10 to minus 5 electron volt. And that cannot form a BC. So that's the claim of Booth's paper, basically.
So do you know what's the new paper is all about, the Witten's paper?
Which one?
The today's Witten's
paper. Witten's paper. So Witten basically, so they calculate various, they calculate some limits. Actually, one limit is that how big or how small can the dark matter halo be. And they find that, I mean, this is just the mass of the dark matter particle, right? It doesn't tell anything about the size of the hole. So they find that, interestingly, I have not completely read it, it just appeared today or last night. So what they claim is that you cannot form halos smaller than 10⁻⁷ solar masses if you have this minus 22 electron volt. So it turns out that, okay, I'll show you later, there's a mass radius relationship. The radius actually is larger if the mass is smaller. It's inversely proportional. So it's like if you have smaller masses, then the halos tend to be bigger. And because
that's just because the de Broglie.
Yeah, de Broglie.
Exactly, yeah. So
that's just the Bose-Einstein Condensate. You saw like the NFW halo on the outside, right? For this relation.
This is not an NFW halo because we're trying to avoid the NFW profile. NFW profile is a Cusp profile.
You have the Bose-Einstein Condensate will like make the core and then eventually put it in.
Eventually it becomes like an FW at larger radius, yeah. But smaller radius, this is a different profile. I'll show the form of the profile. This is like a sine KR over KR kind of profile. Yeah.
So Louis,
actually, to answer your question, I think I reserved that Witten paper. There's really nothing new in it.
So, but 10 to the power minus 7 solar mass, I thought it's already
the same thing.
Same
I
thing.
think they just kind of rehashed it. I don't think there's anything brand new in that paper.
But well, I think they also kind of justify how you can have axion dark matter with this mass quantum string theory models.
Yeah, but
so that part I didn't understand actually. So.
No, but people already looked for this super light dark matter from string theory models.
Right.
So there
okay,
are.
so okay, I'm not an expert.
But actually, we're not. Yeah, we're just.
But okay, since it's Witten, okay,
no,
maybe there is something new. I don't know. We have to read the whole paper. Like, yeah, I didn't do that. Yeah. Okay. So let me see what else. Yeah. Okay. So now, if you compare this BC dark matter versus the core dark matter, then you see that at large scales there is basically no difference. And this has been actually proved by full-phased simulation by this group, which appeared in Nature Physics in 2014. So they did the full simulation with this BC dark matter with like one real scalar field and so on, including all the quantum corrections, effects, and everything. And this is what they find, that if you look at very large scales, then they look pretty much similar. But then if you zoom it in, then at smaller scales, like inside the galaxies, they differ radically. Okay, so this is a scale, I don't know if you can see it, this is 200 kiloparsec here. So if you zoom again further, 50 kiloparsec, and you zoom it further to 5 kiloparsec, and you see that there is now a core structure, and so it's no longer Cusp profile, it's kind of a flatter profile at lower scales. And then, okay, so you can see all these kind of different kind of structures. So this is different from the core dark matter simulations, definitely, okay? And then people have claimed that this kind of dark matter actually solves all the small scale structure problems that I mentioned earlier. There have been many papers on this topic. There's been a review also, a very nice review by these guys on this. I'm not going to show any details of this. I'm not an expert on this. I just take their result at face value, and we believe that, okay, so this is probably one kind of natural candidate where you can solve these small scale structure problems. So if you want to know the concrete particle physics examples, one example I already mentioned is the axion, but in general, they are the so-called WIPs, weakly interacting slim particles, not massive particles, but slim particles. So one example is of course axion, but there are other examples like some you can have some spin 1 fields also in string theory, and I think this is also one of the things that in Witten's paper they mentioned. But there are also like many other like, in general axion-like particles, not just UC axion. So there are concrete examples. But here I'm not going into any particular model. So I'll just take kind of model-independent approach, and I'll just assume that we have a BC dark matter halo, and then how we can constrain it using gravitational waves. So I'll just start with a very simple picture. So I'll describe this whole BC dynamics by using a single classical scalar field. And so the important thing is it is a classical scalar field, it's not a quantum field, because since this is like kind of a macroscopic system, you can explain its full dynamics using a classical field theory. And this was shown by Mark Hertzberg very recently, that the quantum effects are actually here very small. So we take this classical scalar field minimally coupled to gravity, just to this term, and then you have the mass term, and then add a self-interaction term. So this is actually very similar. So if you don't have this term, this is very similar to the Ginsburg-Landau free space energy density in a superfluid, neutral superfluid. And then I just add another kind of 5-fold interaction. And then we calculate the stress energy tensor for this, which is the standard formula for that. If you have this mean background field, you take the G mu nu to be exactly equal to eta mu nu, the Minkowski, the flat Minkowski metric, and then you get this equation of state. So rho 0 is basically the 0, 0 component of the stress energy tensor, and then P0 is the II component. Then they are related by this way. Okay, so P0 is basically lambda over m4 times rho naught squared. And then you can calculate the speed of sound in the medium, in the BC medium, which is basically the partial derivative, square root, and then this is the formula. This is all standard stuff. Okay. And now, what happens if you have a gravitational wave in the medium? So if you have gravitational wave, then they carry these small space-time distortions, as you know, that you can write it this G mu nu as eta mu nu plus some small correction H mu nu. This is usually very small, so the effect is usually negligible in all matter, and that's why it took so long to detect them. But what happens in BC is that all the ground, BC has the ground state, which is very high occupancy number. So it can, so these gravitational waves can actually excite the whole ground state, and this is basically ground state phononic excitations. That means that there's basically density fluctuations in the BC, and so you take the ground state of that, and then because this is long range, because there's a long range correlation, and because gravity wave is long range, then if you have the gravity wave propagating through the BC, you can excite the whole ground state of the BC. And that's the crucial difference between a BC and a normal matter. Okay. So in some sense, like like having this kind of gravitational wave propagating, and then the ground state phonons are kind of being disturbed, and because so now it creates a density fluctuation, you have these kind of excitations. That's the basic picture. And then we can compute actually that what's the effective space-time metric that these phonons will fill, and people have computed that actually, and you find that this is actually dependent on the speed of sound in the BC medium. Okay. And the speed of sound, if you remember, is related to the pressure and the density. And then from the equation of state is related to the mass of the dark matter particle. So that's the crucial point. And then you can use this kind of effective metric and plug it back to the stress energy tensor, and you can calculate the modified equation of state. Okay, so now you find that the equation of state is a bit more complicated, but you can recast it into the background equation of state, but now with a different density. Okay, so before I had this rho naught here, but now I have rho, and this rho is related to this speed of sound in the medium. So this has a back reaction effect on the gravitational waves, because this excitation causes some energy, and that energy has to come from somewhere, right? Because of energy conservation. So this energy is actually lost by the gravitational waves. So the gravitational waves excite this medium. In that process, they lose energy. In that process, they slow down. Okay, so that's the basic strategy. So here you can calculate what's the effective change in the energy density. You just compare with the background equation of state, this new equation of state, and you find that now this rho, the effective density is now kappa times rho naught. This kappa is some factor which is larger than 1. And then the gravitational waves will fill this enhanced density by the refractive index. So the refractive index, this is the general formula for the refractive index for a gravitational wave, which as you can expect, this is always band suppressed. But then because this rho is now enhanced, so this could actually enhance the whole effect. Okay. So then this will basically change the speed of the gravitational waves. If the speed is basically 1 over the refractive index, I'm taking here c equal to 1 in units. So there is no c appearing here. So you can calculate what's the change in the refractive index, which is this. and then from that you calculate what's the change in the speed, which is basically one of them. So here you can see that because of this enhancement factor kappa, this can actually fight against the suppression by M Planck. And this enhancement factor could be huge. In fact, we calculated that for a normal halo size, this enhancement factor is like 10^10. So it's a huge factor. And here also I should mention that there is also dependence on the frequency of the gravitational waves. So if you go to smaller frequencies, then this enhancement will further increase. Okay. So for the current LIGO sensitivity, this is the number I quoted. The enhancement is like 10. The whole enhancement is 10^10 or something. But if you go to lower frequencies, since this is frequency squared, so if you go down by 1 order of magnitude, then this will increase by 2 orders of magnitude. So in fact, if you go to like the space-based interferometers like LISA, where they can probe like millihertz frequencies, 3 orders of magnitude enhancement. So here you get 6 orders of magnitude enhancement for the change in the speed. So that's even better. Okay, so now we take kind of spherical spherical dark matter halo for simplicity. So if you assume a spherical halo of radius r in the line of sight of the gravitational waves which are coming from a distant source, which is at a distance d, capital D. And then the average fraction of the distance the gravitational wave travels through the halo, you can calculate. This is like 4r/πd. This 4/π is basically the average distance it will travel. You just integrate basically. So you take each distance and then you take the average, you can take 4r/π. And then the effective speed of the gravitational waves will then be given by like the speed in the vacuum plus so you calculate how much time it travels through vacuum and how much time it travels through this medium, and then you multiply with the respective speeds, and then this is what you get. This is the effective speed, which depends on this fraction, and then you calculate the change in the speed, which is basically delta Cg, which is C minus C effective, essentially, and that's given by this formula. So this is our central formula. It's a very simple formula. Okay? So the change in the speed will basically depend on the fraction, how much fraction it goes through this dark matter halo, and it depends on how much is the change in the refractive index, basically, which depends on the dark matter properties, only the mass and the interaction strength. These are the only two quantities for the dark matter that are relevant. Okay. So any questions so far?
So it will be dependent on what kind of dark matter particle. Like it's a suppose it's a Majorana or the nature of the dark matter.
So here this has to be scalar dark matter because we are talking about a BC halo. So it should be a scalar dark matter. But whether it's a real scalar or complex scalar, it doesn't matter at this stage. So only some coefficients will change actually. If it's complex scalar, I think you'll get some factors of 2 somewhere. But that's in this calculation that's almost irrelevant. Just trying to do some qualitative analysis here. Right. But that's actually a good point. For fermions, also you can have condensates.
Exactly.
Like you have these Cooper pairs.
Exactly.
Right?
So what would happen in those cases?
Yes. So this is something actually I'm currently investigating. So I don't have a final answer, but I think for fermions also you can have this kind of effect. But I don't know. People have talked about fermion dark matter and fermions forming such large, like you can have fermion condensate at such large scales, like halo size fermion condensates. This. I didn't know about this, but recently I found a couple of papers where they do study this, and they find that it's possible, and they do it in the model. This what is this called? NJL model, the Nambu-Jonah-Lasinio model. So there they study this effect. But I don't know yet how much will that. I mean, how much of this analysis should be valid in that model. I have not studied that in details, but it is possible for fermions also. So it might be interesting to see actually how to distinguish maybe scalar dark matter from the fermion by looking at the different changes.
Actually, one more question. So you said there's this Hertzberg paper that said the quantum effects in the sky were small. Can you remind me why that happened again?
Okay, because
people study these scalar fields a lot in cosmology.
Right, exactly. So here what happens is that you have this macroscopic wave function. Okay, if you have these long range correlations, it behaves like a classical system basically. So it's like all this. So this bunch of quantum particles, they're all in the ground state, and if all of them are in the ground state of the wave function, then they basically behave like a classical system. So you can treat this whole thing as like a single classical scalar field, like a big scalar classical wave function instead of individual quantum wave functions. Right. So that's the basic idea.
So that's straightforward. There's nothing tricky about it.
No, there's nothing tricky there.
Okay.
Okay, so now, so now to calculate this term, so this is what basically I'll be doing in the rest of my talk. I'll be calculating this effective change in the speed of gravitational waves, which depends on the parameters of the halo. There are only two parameters, mass and the interaction strength. Okay, so now let's look at these halo properties. One thing is that you have this mass radius relationship, which I was mentioning before. That what happens in ordinary dark matter halo, you have like some mass for the halo and you have some radius. They are independent parameters. But what happens here that they are not independent. The mass is actually dependent on the radius, and the radius is actually inversely proportional to the mass, to give some power. So that means that if you have larger masses, then they will form smaller halos. And if you have smaller masses, they will form larger halos. Yeah, you said that basically comes from the de Broglie equivalent relationship. So now, how to calculate this? So here, this parameter called AS, which is the S wave scattering length, and that you can calculate in the low energy limit. That if you take the zero wave number limit, then this is the cross section for 2x2 scatterings for the lambda phi 4 theory, and that cross section is basically 4 pi times a square. And then you know the cross section, you can calculate it analytically for a lambda phi 4 interaction. That's a standard textbook calculation, and then you plug it in, and then you find this AS in terms of this lambda mass, and then you plug it in here, and you find that the radius is given by this formula. It only depends on the mass and the self-interaction strength of the dark matter particles. And then for the density distribution, somebody is asking what's the density function here. So in this case, so here the density distribution of the spherical symmetric halo can be written in this form. So you have some central density, and then instead of this NFW profile, you have this kind of sine KR over KR profile. So this basically makes it like flatter towards the center, but it behaves like the usual 1 over r if you go higher radius. Okay? And this k is basically it's pi over this actual radius. And the central radius, these people have done simulations, and then so kind of the best fit is like 10304 solar mass per parsec cube. And then you can calculate what's the average density. You just do the integration for the you take this one, you just do the integration for the whole 0 to capital R, and this is what you get. So this is the number that actually I'll be using in the numerical analysis. So we have this rho 0 in the equation of state, and this is the number that I'll be using for the average density, the halo. So now let me go straight to the results. But what we get, so this is kind of a BG figure, but I'll try to explain one by one each one of them. I didn't have time to actually separate all of them out and make different figures. Okay, so we just take some basic parameters that from the LIGO observation, that the distance from where the gravitational wave is coming, we just take 400 megaparsec. This is actually the first LIGO event where the black hole merger was at 400 megaparsec. So this is what we take. And for frequency, we just choose some fixed value, 35 hertz. But you can vary it from, in the whole LIGO range is like 35 hertz to 500 hertz or something like that. So we can vary it over that range. But the timing is just fix it here. And then what we find is that if the change in the speed of the gravitational waves was larger than 10 to minus 36, I'll answer why it's minus 36 and not larger than that. But for the time being, let's just accept this number. So if the speed was larger than that, then you can actually exclude this part of the parameter space in the mass versus coupling plane. Okay. And if the speed,
how do you exclude it? Like, what's the?
No, so because in this part of the parameter space, the speed, it turns out that the speed of the gravitational, the change in the speed of gravitational waves is larger than this. So if you measure the change in the speed to be smaller than this number, then this part is excluded, right? So that's the idea. And then if this was, even you measure it into more and more accuracy, you go minus 40, then you exclude the larger part of the parameter space. And this goes on, okay? And then why we can't go above minus 36? Well, so actually, so if you
So,
look at
but
this,
also you have a BBN constraint.
yeah, I'll explain all of that. Yeah, so I'm just explaining one by one. So here from so if you look at this expression, then from here and using this mass radius relationship, we find that there's actually a maximum value of delta Cg that you can probe using this method. So if the delta Cg was larger than this particular number, then this method doesn't work. I mean, basically this doesn't put any constraint on the system. So and for this particular frequency, we find that this maximum number is this 10 to minus 36. So that's why so we have to go to that level of sensitivity if we want to use this approach to probe BC dark matter. And just to compare the current level of sensitivity from like model independent sensitivity like 10 to minus 15, excluding LIGO. So there have been analysis using I think gravitational waves constrained from Cherenkov radiations and so on. So they have put limits of 10 to minus 15. But if you use the LIGO sensitivity, then you can actually go down to minus 40. So that's why I have shown this 10 to minus 40 here. Okay, so now let me try to explain the other lines here. So, okay, first let's look at this blue line. So this band is basically where the cross section over the mass is in the range of 0.01 to 1 centimeter square per gram. So this is the favored range of sigma over m for self-interacting dark matter. This is from various different constraints. Mainly constraint comes from bullet cluster, because if you have self-interacting dark matter, then you have stringent constraints for bullet cluster, because there you don't see that much of like this. You don't see that much of colliding dark matter. And then also people have studied the halo shapes and different stuff, and they have come up with this. This is the best fit kind of parameter space. And then there is another kind of curve here. This kind of dark green curve. Sorry, where is that here? So this is kind of superimposed on another curve, but so this is called the dwarf spheroids. So here you basically fit the rotation curves of the dwarf spheroidal galaxies, and then you get this radius of around 0.5 to 10 kiloparsec for the dwarf spheroids. And because the radius has a relationship with the mass, from this you can actually put a constraint on the mass over the coupling to the power 1/4 to be in this particular range, 4 to 18 electron volt, and that's what is shown in this in this band. So basically, when this the band where the self interaction cross section is right value, and this band where the rotation curves are fit, so that basically gives the kind of region which is physically interesting for us to study. Okay, so that's what is this yellow point.
So, but if I use those 10 to the power minus 22 EV, then I don't look at the at least those colored or BBS.
No. So if you look at 10 to minus 22, then you are actually looking at very, very small values of the coupling, right? It's almost like non-interacting scenario. Yeah. So there basically, yeah. So I mean, of course, you can still use this constraint here. You can almost exclude this actually. But the other ones won't be applicable, because these limits are for self-interacting dark matter, right? Because the sigma over m.
So is there any allowed parameter space for 10 to the power minus 22?
Yeah. So if you just remove all the like whatever constraints are obtained for self-interacting dark matter, so you just remove those constraints, and but the other constraints are still applicable, right?
But still there is some parameter space left.
Yes. Well, so there you don't have like this two-dimensional plot. You just have like one mass, and
yeah. So, but I don't see that 10 to the minus 22 to that.
This is 10 to minus 23 actually. So yeah, this is minus 22. Yeah, but the coupling is the. I mean, this doesn't have any meaning right there, because there's no interaction there. So yeah, you have to kind of like maybe draw another picture. So this picture is valid only for like the model where you have the self interaction process. Where you have the self interaction, right? Okay, so now let me see. So there is another constraint here. This is a theoretical constraint actually. So in this part of the parameter space, the relaxation time required for this virialized dark matter clumps to form a BC is larger than the age of the universe. So that means that this kind of this BC dark matter cannot form in this part of the parameter space. So the coupling has to be larger than certain value. This repulsive interaction has to be larger than some certain value for this relaxation time to be smaller than the edge of the universe. Okay, so that's why. So this part is excluded. And then.
But that's only because you want it to be self-interacting, right? I mean, it can be there, but it just...
Yeah, so if it is not self-interacting, then it can only work for mass equal to 10 to the minus 22 electron volt. So if you want to work it for different masses, then you must have this positive self-interaction, right? That's what I was emphasizing before, and this is what basically, yeah, this you can already see in this kind of parameter space.
Should I understand that here that the T relaxer and the T universe, like your halo is still relaxing, so basically is that just this method doesn't work for detecting it? And that's
No. So this halo doesn't form a BC. It just like there are some kind of loose particles just moving around, but they don't have any long range correlation. They don't form a BC. So to form a BC, you need to have the relaxation time smaller than the edge of the universe, right?
But it can still like exist as like a dark
Like,
matter.
it's just,
Well,
it's like
it
a
doesn't
halo.
It's like a dark matter halo, but it's not a BC dark matter.
Yeah.
I mean, there is no condensate, so to say. Right?
But that's fine, you know, maybe that's...
Well, that's fine,
Yeah.
but then it's not. It's just like a normal dark matter halo. Then
Oh,
it's
yeah.
like a cold dark matter halo,
Yeah.
and that doesn't solve the small scale structure.
Oh, yeah.
So that's why. So that was my original motivation. That yeah. So you want to have like a BC dark matter halo. Then only you can see this effect. Well, if it's a normal dark matter halo, you don't see this effect, right? Because they're not excited like on. I mean, all of the dark matter is not excited.
I mean, is the way to think about, if you have to previous one, is a way to think about that space below your, that's just like axial, that's just like normal axioms, right?
Uh,
Yeah, right.
Something similar, yeah. So it's like, yeah, you don't have this kind of condensate, but you have like loose dark matter particles in the halo hanging around. Right. Yeah. Okay, and then, okay, so it seems like, oh, this is also consistent with the BBN constraints on light degrees of freedom and so on, so we don't have to worry about that. Then I talked about the relaxation time, and then there is another constraint where I call it the TC at z equal to 0.1. So basically, so this event that LIGO has seen, so this was at the redshift of z equal to 0.09. So equal to 0.1. So in this part of the parameter space, what happens is that the critical temperature for the BC to form is actually below the temperature at z equal to 0.1. So that means that if you are in this part of the parameter space, then this BC dark matter halo could not have formed at the time this black hole merger happened. So that means that then there is no such BC halo, and you don't have this effect for the gravitational waves. So you like the halo to have formed before this merger event happened, and that's why this part is excluded.
It doesn't really seem like it's excluded that part of the parameter space. It just says like, if the event happened here, you're basically like black hole event just doesn't tell you anything about the model.
No, so okay, so what I'm saying is that so we start at the event from the source, and then in between it passes through this halo, right? So if this halo didn't exist the time it is passing through, then you basically don't have any constraints. So in some, okay, so I should agree. So it's not like it's excluded, but the thing is that in this part of the parameter space we cannot apply our analysis basically, right? In that sense, yeah, that's right. And then this becomes actually a bit slightly stronger if you assume that these dark matter particles are thermalized. I mean, in this particular construction I have, they have no interaction with the standard model degrees of freedom. So they cannot really thermalize with the thermal plasma. But if you add some other interaction terms and you say that okay, this is actually thermalized, then you require that this kind of structure must form before BBN, right? Otherwise it will spoil BBN. So that actually puts a slightly stronger constraint here. Otherwise, these things will actually form after BBN, and then you don't have basically dark matter during BBN. So that's kind of slightly strong. Okay, and then there's the critical temperature formula, which was actually, I was surprised that this kind of critical temperature formula was derived back in '74 by Weinberg and by Dolan and Dacue. So that time nobody knew about maybe BC dark matter, but these guys just computed the critical temperature for a self-interacting scalar system and Fermion system. So and then you have another line here, this kind of cyan line, where I say the average halo size is larger than 1 megaparsec, and this kind of parameter space is kind of unrealistic because the kind of dark matter halo that we are talking about here, they're kind of kiloparsec size dark matter halo, which is actually this part of the parameter space. This is favored by the simulations. So if you have a dark matter halo size larger than like megaparsec, that's unrealistic, and that actually rules. So this part of the parameter space is kind of that sense. Okay. So we are essentially looking at. We're interested basically in this part of the parameter space where all the simulations are consistent with each other, and then you can explain all these small scale structure anomalies. So from this figure, we basically conclude that if you measure the change in the speed of gravitational waves up to the accuracy of the 1 part in 10 raised to 36 to 10 raised to 40, then you can completely prove this kind of scenario. So that's the bottom line.
So is it just saying like LIGO would rule out that area of parameter space?
Yes. So yeah, that brings me to the final topic about this multi-messenger approach. So how we go to delta CG 10 raised to minus 36. So as I said, the current limit is actually something like 10 raised to minus 15 before LIGO. Okay, this was from constraints on the sudden co-radiation triggered by the gravitational waves. And so then immediately after the LIGO discovery, Fermi, the gamma ray burst monitor announced that they have observed one candidate event, one gamma ray event, I think 50 keV event, within I think 0.4 seconds of the LIGO event. Okay, so then there's the immediate suspicion was that maybe these two events are correlated with each other or not, and then people actually use that to kind of constrain the speed of gravitational waves. Because if you have like this multi-messenger approach, then you measure the gravitational waves, and if you also measure another kind of like either photons, X-rays or cosmic rays, neutrinos, whatever. So another kind of messenger, and then you compare the speeds, and then from that you can actually constrain the speed of gravitational waves. And people have done that analysis, and the numbers are kind of slightly different, but there was one analysis here which claimed that actually if these two events are actually correlated, then you go up to 2 times 10 raised to minus 40. And I mean that's the limit you can put on the speed of gravitational waves. Okay? So this is actually very, very bold statement. But then, of course, whether this correlation or not, that has been a controversy since then. And recently there was, I think the latest analysis seems to suggest that this was actually coming from background or not related with the LIGO event. But in future, people have proposed to have this kind of multi-messenger astronomy. This is one collaboration. I think they're trying to have this multi-messenger approach in various different messengers using X-rays, optical, then cosmic rays, and also neutrinos. Okay, people have already started doing that after the second LIGO event was announced. They have already started putting constraints using this multi-messenger approach. So in future, I hope that this approach will be successful, and in that case, if we really have this kind of correlation between the gravitational wave event and another multi-messenger counterpart, then we can actually go up to 10 raised to minus 40, and this is what will be excluded in this part of the parameter. So this can be completely proved. So yeah, I think that's what I have to say. So yeah, to conclude, I've discussed a new method to probe this BC dark matter using change in the speed of gravitational waves. And the good thing about this is that this deviation in the speed of gravitational waves only depends on two parameters: the mass and the self-interaction strength, and of course the frequency of the gravitational waves. But it doesn't depend on any other details of the model or any particular mechanism. So as a physically interesting region of this parameter space, as I mentioned, it can be completely probed if you can go with the sensitivity up to 10 raised to minus 36 to minus 40 for the LIGO frequency range. And as I mentioned, since this is 1 over frequency square, so if you go to Lisa frequency, then this can be actually brought down to like 10 raised to minus 27 or minus 28. So that's even more promising. And that should be soon achievable in this multi-messenger approach if they really find some correlations between the gravitational wave signal and another multi-messenger counterpart.